So I've got a set, which is a pile of stuff. It's things. But I want to do things. I want to perform operations with those things. I need to really dig into what does it mean to have an operation? This sounds way too elementary, but I promise there's some actual deep questions here. Binary operation is a function. It takes in two things, an ordered pair, that's why it's from our Cartesian product, and spits out an element within that same set. Now, when I think of a function that operates on ordered pairs, I start thinking about Calc 3, or I start thinking about f of xy, right? I get that. You take two real numbers, you do something, you get out another number. That notation, that functional notation, is a good idea, but it's not going to help us, because the other way we think of an operation is to do something. I give you two numbers and tell you to add them. Where do you write the operation? That's not a rhetorical question. Where do you write the operation? Between them. But we don't have to, right? I mean, for every ordered pair in my Cartesian product, I'm going to call my function, instead of f or plus, I'm going to call it star. If I wrote this like a function, I would write star of the ordered pair AB. I don't like that. I would rather, exactly as you said, Roman, write A star B, put it in the middle. And then this says, what I'm really doing is I'm doing this function on A and B, but I write it with that. This is referred to as mid-fix notation. And this version is prefix notation, because you tell me the operation before you tell me what I'm doing it to. There is something called postfix notation, where I give you the two things and then tell you what to do to them. And you literally write it A, comma, B, comma, star. If you use postfix notation in regular, ordinary arithmetic, you never need parentheses. Ever. There are calculators that do that. This is the original notation where you put it in the middle, and where you put it in the front was called Polish notation, where you'd say, I'm going to add 2 and 3. Postfix notation would say, here's 2, here's 3, add them. So it's called reverse Polish notation. If you ever get a calculator that says RPN on it, that's what it means. I have 2 of them. It's weird. So when I think of adding is an operation. You take in 2 numbers, you spit out another one. Multiplying. Subtracting, order matters, right? That's why I need to write it this way, so I know which one is going where. But in order for a binary operation to be defined appropriately, it really has to work for every ordered pair. And that's why, while I did say adding and subtracting, multiplying, didn't say dividing. Why? Well, but it matters in subtraction too, right? I can subtract any two numbers. I can add any two numbers. I multiply any two numbers. Can I divide any two? Which one's going to screw me up? Ah, okay. If I write my operation to be division, that doesn't work. Star to 0 doesn't make sense. Talk to me.
Could you still do a prefix notation when you define A, B as being not equal to 0?
So if I change my set, I can make things work. So I could change that, right? Now I don't have 0 in the set. Does it work there? Yes. If I change my set, things work. Did y'all take linear algebra? You're in it now. Jack, you took that, right?
Yeah.
Okay. So if you've just started linear algebra, then you might not have matrices down. But matrices are going to be a good example of some things we're going to do. So matrix arithmetic is going to come up occasionally. Matrix arithmetic is another one that has to have restrictions on the set in order to work. A matrix is an array of numbers, right? You got to that part?
We just talked about it.
Good, perfect, I love it. So if I consider the set of matrices with real entries, if I want to add matrices, I need to add all the pieces that are in the same places. Did you do that one yet, or is that still coming? You haven't added matrices?
No, like she basically explained what a matrix is.
Okay. Arithmetic on matrices is coming. When you add matrices, you want to add the things in the same places, which means you can't add any two matrices. They have to be the same number of rows and the same number of columns. Otherwise, there isn't a matchup. Oh, so I could talk about adding 2x2 matrices, or 2x6 matrices, or 3x4 matrices, but I can't add a 3x2 matrix and a 1x7 matrix because the dimensions don't line up. So Roman, that's exactly the right idea. If it doesn't work all the time, maybe I can make a restriction, or maybe I can change the operation slightly to make it so that it can work. So the other part of this is that I need to make sure that what I get out is still in that same set, right? Because the binary operation goes from S cross S to S. If I'm dealing with non-zero numbers and I'm dividing, I can't get zero. Whether zero, because to be zero, we'd have to get zero on the top, and I didn't have a zero to put there. Yep. Happens when you run into things. So I'm going to talk about a binary operation on a set, because we really only deal with one set per operation. Some operations are defined the same way on lots of different sets, but whenever we are looking at a specific operation, we're looking at it in the context of a particular set. So if I talk about addition, I want to talk about the things I am adding, whether those are vectors, matrices, numbers, integers, rational numbers, complex numbers. I can do addition in all of those ideas. I can do addition in strings. CS strings. What's a string in computer science programming? String is just a list of letters and numbers, spaces and characters. To add them literally means to write one directly after the other. You get a longer string. I have 3 letters over here. I take these 3 letters, I add them together, I get a 6-letter string. I can add. It's a weird definition of adding, but it's a definition of adding. I want to look at a subset of S. Some subsets are nicer than others. A binary operation acts on our set. Now, if I just look at the subset H, H is closed under my operation. If every time I operate on things in H, I stay in H. I'm going to pick a nice, easy operation. Addition on the integers. Now let's pick a subset of the integers. And we have lots of choices here. Give me a number. 7. Let's consider the subset consisting of all multiples of 7. So Santino, here's my question. If you take any two numbers in that set and add them, must the result still be in that set?
Yeah.
Why?
No.
Right, but how do I show that no matter what I do, when I add, the answer is still a multiple of 7? This is where I get to be a pain in the ass and say, I need to actually prove this like I proved stuff out in the street. So let me think about how we can go about this. But that's an infinite set, so I can't do all of them. So let me rough out what a proof might look like. Suppose I pick two numbers from my set. But my set only consists of multiples of 7. Which means, what do I know about A? It's a multiple of 7, so it's 7 times something. And if I take out the 7, I got to be left with an even number, a whole number, not an even number, an integer, n1. Same thing is true for B, right? Because B is in my set H. So now if I think about adding, I can factor out the 7. And what happens when you add two integers? Eek. Away.
So,
It's still an integer. So A plus B is a multiple of 7, which means it's part of my set. The hard part is looking at the answer and making sure it's in the set you want it to be in. So, still with addition, let me give you an example of a set that's not closed. Here's a set of odd integers. Is this set closed under addition? Because if you add two odd numbers, what do you get? Well, just pick one example, add two of them, and it doesn't work, it's not closed. This is a universal statement, right? Being closed means for all AB, which means I want to show it's true, I have to prove it. If I want to show it's false, I have to find one counterexample. I'm gonna look at weird sets. I'm gonna look at weird operations. So these are rigged in a lot of cases. And some of them may look like they don't have any real purpose. That doesn't mean they don't, it just means that purpose isn't obvious. And sometimes the purpose is there just to mess with us so that we think about whether or not this is actually going to work or not. Questions? I think these are all in the same set. It's the integers or is it the positive integers? This is what I get for not making a note. Positive integers. I could define an operation that just says pick the smaller one. I mean, that's really what this function does, right? It picks the smaller of two numbers. I don't know why you might want to do that, but you could. There are places where that's the right thing to do. We'll talk about weighting problems in some other courses. We're trying to construct the smallest or cheapest network out of things. Well, picking the smallest thing is an important thing to do. It's a sorting algorithm. I could say, pick the first one. Whichever one's on the left, that's the one I want. I could say, pick the smaller one and then add 2. Okay. Here's a question for you. In the first and the third one, what happens if I change the order of the numbers? In the first one, I say pick the smaller of A and B. Does it matter if I switch the numbers around? What about the middle one?
Operation.
That operation right there. The operation says A star B is A every time. 2 star 5 is 2. 7 star 3 is 7. 14 star 108 is 14.
Yeah, running at a
Yeah. 2 star 5 is 2, but 5 star 2 is 5. Whichever one came in first. Whichever was the aha. It would be nice if my operation would always flip-flop. But clearly I have operations that don't, right? So ones that do have a nice property, let's write that property down. That being able to flip the numbers is called the commutative property. Now, commutative properties were things I talked about with just doing ordinary numbers. And then there was this idea of associative property that I could put parentheses. If you add 2 and 3 and 5, does it matter what order you do them in? 2 plus 3, then add 5, or 3 plus 5 and then add 2. So you can put the parentheses wherever you want it, but that doesn't always work either. By the way, this third operation we had here, that one fails to be associative. Let's check. If A star B equals min AB plus 2, we're going to do 2 star 5 star 9, and we're going to do 2 star 5 star 9. Hi. No worries. Thank you. If the operation is take the smaller one and add 2, then this becomes 4 star 9. 4 star 9, take the smaller, add 2, we get 6. If this is done first, what's 5 star 9? 7. But 2 star 7, they're different. And again, if I find one out of place example, it can't be associative, because associative and commutative are universal problems. This, by the way, actually means that when I write an expression like this, in a non-associative operation, that doesn't make sense. I need to know where the parentheses are unless I know it's associative. Questions? So far, so good? The purpose of making this idea as general as possible is to be able to say in the long run that the operations I use on a regular basis are as nice as they can be. Adding, multiplying, ordinary arithmetic, we do this stuff all the time. It works great. It makes sense. There are exceptions. 0 is a problem when I go to do dividing. But there are behaviors that I want to make sure my sets have. I'm going to apply this to weirder and weirder things, like strings, like arrangements. There are 3 of them. How many different ways can I line that one? You know the answer to that question. That wasn't the street question. How many ways can I line the 3 of you up? Why?
There's 3 of us in 3 different positions with me.
Yeah, but if I put you in position 1, can I then put you in position 2? You're already over there in position 1. You can't also be in position 2. So there's a limitation. Multiplication principle would work if I could repeat. Not allowed to repeat, there are only 6, right? 3 first choice, 2 second, 1 third. Great. But I can think of those 3 lists. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, right? I can go through and I can list all of those options. I think of those 3 lists as objects in a set. And now I can think of those 3 objects, and I can try and define an operation on them. Or those 6 objects. And it turns out that that sort of set and that collection of objects have some very good operations that are really, really useful. Because they define objects in real life. How many of you used a VR headset? I cannot use one well, both because of my glasses and they hurt my head. But when you reach out and pick up an object in that VR environment and move it, the computer has to do all of that, right? It's got to recognize and project into that screen where that object is. And if you move, it's got to track all those objects. That's the big version of rearranging the space around you. And it starts with rearranging 3 objects. So I do it with just those 3 things. You all are my target audience here, literally. How do I make that operation make sense? So I like operations that are commutative. I like operations that are associative. Some of my favorite operations turn out to be non-commutative. Calc 3. Yes?
Where?
Yes. Cross product. A cross B goes one direction. B cross A goes the other direction, right? Cross product's a beautiful operation on vectors, but it's not commutative. That extra minus sign hits me up. So if I'm working with a set and an operation, if operating with this element doesn't change the thing you started with. Again, we've seen these before. Regular, ordinary arithmetic. Pick a set of numbers that you like. And pick an operation on them. Ordinary, regular numbers. We can use integers. If I'm adding integers, is there an identity element? What's something you add that doesn't change anything? 0. Pick any number, add 0, you get the same number back. Pick any number, add 0. It needs to equal the elements I started with. Realize I didn't write all 3 conditions down. And it shouldn't matter which side you do it on. If you have an identity, it should work on the left or on the right. And it doesn't matter whether I add 0 to a number or I add the number to 0, it still gives me the same number. And it doesn't have to be integers, right? This works in the real numbers, this works in the complex numbers, this works in the rational numbers, because 0 is in all of those things. If I'm multiplying, what's my identity element? I change the operation, change the identity element. It'll be 1, because multiplying by 1 doesn't change anything. No matter what number you give me, if I multiply it by 1, or if I take 1 and multiply by that number, I get that original number back. Functions. Way back in algebra class, we took f of x plus g of x and defined a new function, f plus g. If I take the function whose output is equal to 0 everywhere, let's call it z of x. And z is a function from the real numbers to the real numbers. Then I can think of that function as the identity in the universe of functions. In the set of functions from R to R, I will call this set FR. Where f plus g of x is f of x plus g of x, then z of x is an identity element for the operation of addition. Because you're not just adding 0 at one spot, you're adding 0 everywhere. Now, again, that's not a universe we think of working in all that often. But we do a lot of operations on functions, right? All of calculus, taking derivatives, taking integrals, that's operations in functions, right? As a matter of fact, the set of functions f that have derivatives everywhere makes up a whole new subset, right? Because in order for a function to have a derivative, it's got to be continuous. It's got to not have corners, right? It's got to not have jumps or gaps. Okay, I got all sorts of issues there. Differentiable functions make a subset. Under this operation, z is still an identity there. The sum of 2 differentiable functions is again a differentiable function. Why do I know that? Chapter 3, rules for derivatives. F plus g prime is f prime plus g prime. So it stays closed. Like this. Questions? It's weird. It's not quite concrete yet. Still very mushy. That word right there. An identity. Hints to me that it's possible that I might have more than one. Otherwise, I should have said the identity. Highlander. There can be only one. I'm sorry, that movie's older than you are. I think the TV show's even older than you are. I claim that identity element is unique. Crap. We did uniqueness proofs in discrete too. How the hell did we do a unique? I know that we did them. I just have to remember how. These were almost always proofs by contradiction. So I'm going to assume there are two of them and show that they can't be different. So let's suppose I have two of them and they're different. E and E prime. If you don't like using E prime, feel free to use F or I or something else. Doesn't matter. What's it mean for E to be an identity? The definition of being an identity is that
For like an identity for an element, like.
right. This E right here, I said it's an identity. What does that mean?
I don't know how to say that.
Then let's go right back to our formal definition that we wrote down. It's an identity element. If I multiply anything by it, star by it, I get the same thing back. If I star E with anything, regardless which side I put it on, I get that thing back. So if I take E and star it with anything, I should get that thing back. But I also said that E prime is an identity, right? Which means the same thing. Now, I was a little sneaky here. And in that first line, I wrote E star S. And then the second line, I wrote S star E prime. I picked one for each of them, even though both are true, right? It could be E star S or S star E, but I picked the E on the left. In the second line, I picked the identity to be on the right rather than the left. I just chose that. So here is the $64,000 question. Remember, I said this is a proof by contradiction. So I should get a contradictory statement at some point. I think I get it here. What should the answer to this question be? According to this sentence, the answer should be E prime. But according to this sentence, the answer should be, what does that tell me about those two things? But my assumption was that they were different. There's my contradiction. If there's an identity, there can be at most one. Questions? At most one. That means there is another option. What's the other option? There could be none. I need an example for that to make sense to me. I need an example of a set and an operation that does not have an identity. So let me take a set where I know there is an identity and mess with it. When I'm multiplying normal ordinary integers, what's my identity? 1. So what if I took just the even numbers? Well, if you multiply by any even number, can you ever get the same thing back you started with? There's only one time that happens. If you multiply by 0, you get 0. So 0 times 0 works. But 2 times 0 gives me 0. It never gives me 2. 2 times any other number is never going to give me that original number, is it? 1's not in here. And under multiplication, there's no identity in this segment. Whoa. So having an identity depends on my choice of operation. I choose an operation in my set and I say, is there a thing where I can do the operation and never change what I did it to? Let me think about you three lined up on the wall, and I was talking about rearranging, right? Is there something I can do that doesn't change the arrangement? I could do nothing, right? Okay, ready? Everybody shift nowhere. Then you're rearranged. Um, and the rearrangement, the new output is the same as the input. No matter what I tell you, if I tell you don't go anywhere, it all look the same as when I started. If I'm adding, yes, I can add 0. So as long as 0 is in there, I'm good. The odd numbers are going to be duh, because 0 is not in there. So I would like to know if I've got a working idea for an operation, does it have this property of, hey, this operation does have an identity in our set? Once I have an identity, that ordered pair notation right there tells me I'm going to use the set S under the operation star, whatever it happens to be. I like calling my identity element E. I didn't start that trend. A lot of textbooks use I, but I has a particular meaning, square root of -1. So that tended to fall away pretty quick, and this idea of using E stuck around. If I have an identity, then for X, an element of my set, we define the inverse of X by X prime so that X star X prime equals the identity. And it doesn't matter whether I do the X prime on the left or the X prime on the right. I want it to work the same on both of them. Again, even if I do have an identity, it might be that not every element has an inverse. Think about multiplying again. What is my identity in multiplying? So what if I told you you're only allowed to multiply integers? Pick a number that's not 1. Oh. I don't want to use 0. Pick a non-zero number that isn't 1. What do you do to multiply that and get 1 out?
1/7.
But 1/7 is not an integer, is it? Yeah. So no matter what, well, almost none of the numbers will have an inverse. If I picked 1, 1 times 1 gives me 1. There's one other number where it works. Zero's not in the set. There is one other number where I know I can multiply and still get 1. And I'm being really sneaky here. -1. Because -1 times -1 gives me 1. There are lots of places, lots of situations where we deal with the idea of having an inverse. Now, again, I'm going to drag out of the depths of your memory from discrete last year. Modular arithmetic. We solved equations like 5 times something is equal to 13 mod 100. Or mod 73 or something like that, right? And it only was solvable if 5 had a multiplicative inverse. And we had to use the Euclidean algorithm to figure out what the multiplicative inverse was. And the Bézout coefficient was a long pain in the ass of a problem. That's why we didn't do it on the exams. But we did it. That multiplicative inverse is exactly this idea. Some of the numbers have multiplicative inverses, some don't. It would be nice if all of them did. Gee, I wonder when that's true and when it isn't. Now I can figure out that. And the answer is, it turns out, we can actually figure exactly that out. We can tell when there's an inverse and when there isn't based on, for that idea, the greatest common divisor of 2 numbers. I was able to do that. Questions? When I'm dealing with functions, I do functions on things in my set, but sometimes I do more than one function. And if you think of our operation as a function, I can multiply and then multiply by another number and then multiply by another number, right? I can add and then add again and add again. I could take the smaller one and then take the smaller one again. We did that example, right? That's really composition of functions. You really empty. It turns out that compositions are associative. And that's why I can do A star B star C. but the operation I choose may not generate the same result. The operation itself is definable. Questions? Let's suppose I have a small set. Integers is infinite. Real numbers is infinite. Arrangements of U3, there were only 6 things, right? I'll pick an even smaller set. And I have a binary operation. Well, then it might just be easiest to write out all the possibilities. Now, how the hell would I do writing out all the possible results for star? I'm gonna make your life easy, I hope. I am going to make a definition that in this table, I star j uses the ith row and the jth column. So when I put an answer here, that's A star A. Row, column. Whatever answer is here, that's A star B. Whatever answer is here, that's A star C. So all of these products across that first row, they represent A star A star B, A star C. So the second row is B star A, B star B, and B star C. I am literally just making up a table. But now that I have this table, let me ask you a question. I now know everything that happens when you do this operation star. Is this operation commutative? Again, you answered this question back in discrete. Only we didn't use the word commutative back then. We were talking about relations, and we used the word that I used on Tuesday. Symmetric. And it's actually the symmetry of this table that will allow me to find out if this is commutative. Because that C right there, that's A star B. Right? What's B star A? Huh? A star B is not the same as B star A. And if I go back and I look at the table, I can look at the entries in symmetric positions. Notice also C star A and A star C are different. So there are two different ways I could identify this as a non-commutative operation. Page 15, table 22 and 23 show you a way of saying, oh, if this is commutative, then I can fill in one half of the table from the other. If this is actually a commutative behavior, then that D should have to go there, and that A should have to go there. And I can fill in these upper 6 spaces with the same 6 elements that are down here. Just fold it over that diagonal line. I like operational tables. There are ones that have particularly nice properties that I want to use, and being able to identify those properties from the tables alone is really, really helpful. Questions? I want operations that make sense. And that means this is a function, right? A star B is a function. It's a function from the Cartesian product to the set. In order for this to make sense, every time I put in an ordered pair, I need to get something out. And the thing I get out has to be part of S. So we talk about a function being not everywhere defined. Well, that's a problem, like our division, right? We couldn't divide by 0. So I said, no, we have to change something. If I'm only allowed to work in integers, I can't divide. Because 1/2 is not an integer. So it's not a valid element. It's not everywhere valid. Again, the goal for us is to make sure that all of the operations we want to use satisfy the best possible properties. That means we need to be able to check them and work. 99% of the time. We're going to assume this. I'm going to say, here's the set, here's the operation we're working. It works. But you should be able to check these definitional ideas. It's not going to be always obvious, but it should not be, oh my God, this is a 300-page proof. Shouldn't even be a 10-minute. But it still may very well need to be things that we prove. Questions? So, that table that I made, I pulled stuff out of thin air. What makes one table better than another. In this case, there are 9 different spots in that table for me to fill in. I got 3 options for each one. Realistically, that makes 27 different tables. That's only some of them will be commutative, only some of them will really make sense to use. I could tell you that A star B, A star C, I could tell you that no matter what if I filled in all 9 of those with B? It would work, but it would be stupid, wouldn't it? No matter what you do, the answer is B. That's a really, really great multiple choice exam. Is that useful to me? I want to examine what sort of structures are useful. So the things we've defined today, the idea of being associative and commutative, having identities, having inverses, I like those properties. So what if we used those? How many tables could I get out of the 27 that would satisfy all 4 of those ideas? What if I had 4 things instead of 3? You saw a table with 4 things. It was an example in the textbook. So what if I had A, B, C, and D and I wanted to fill in the table? Well, now there are what, 64 possible tables. How many of them do the nice things? The answer turns out to be a lot smaller than you think. Why? That's Tuesday. But what else is Tuesday? The due date for the first set of homework from section 0. So if you've got questions, come bug me between now and then. I will see you on Tuesday. Have a wonderful week. Like, what's Tuesday? Oh, what did I forget?